We had started talking about function spaces, transformation operator. We touched upon representations a little bit. So, that is what we are going to do today. So, do not lose the sight of why we are doing all this. We are doing all this because we want to develop a systematic and generic description of symmetry operations and point groups, right. So, that we do not have to work out the matrices all the time and we do not have to worry about how many reducible representations, how many irreducible representations there are all the time. We want a machine, a black box which will do it for us once we have prepared it. Right now what we are doing is we are populating the black box, we are building the black box. Once we are done, we can put the lid on it and seal it, and we should not forget about what is inside, but then you will see that the machine can be used even without understanding how it works. Okay. But the thing is, you should not work like that, you should know what is there inside the black box. For all this discussion, we are following this book, Group Theory and Chemistry by David Bishop. Right. This is something that we had talked about in when we met last time, right, long ago. We had talked about a function space. What is a function space? There is no need to be scared because I am using this term space here. A function space is just a collection of functions. For now, let us just call them f1, f2, f3, f4, so on and so forth. A collection that satisfies some properties, and the properties are as follows. If you add two functions, then the sum should also be belong to the same collection. Or in other words, the sum should also be a function in the same function space. Fi plus fj should be equal to fk, where fk also belongs to the same function space, and the very convenient example that we have been using is that of position vectors, right. So, if you add any two position vectors, I think we understand that we are going to get another position vector. What is a position vector? Let us say this is a point, right. You join a line, draw an arrow from the origin to that point. So, since it is an arrow, it is a vector, that is called the position vector for that point. What is the position vector for this point? Let us say I am the origin, this is a position vector, this is a position vector, that is a position vector, so on and so forth. So, if I add this and that vectorially, so I get another vector which is also a position vector, starts at origin and goes somewhere in finite space. So, the position vectors, for example, satisfy this condition that when you add two functions, you get a third, the sum is also a function in the same function space, okay, right. The second thing is, if you multiply a function by a scalar quantity, a number, then what you get is also a function in the same function space. That also is very easily understood by using the example of position vector. 3x, now making it very simple, 3x is a position vector or not? 3e1, let us say, 3e1 is a position vector along x, 23e1 is also a position vector, and 23e1 is 23 divided by 3 into 3e1, okay. Now, third is, if you combine the first two, then what you write is, if you take a linear sum of the functions, then the linear sum of the functions is also a function in the function space. Sum over I, ai fi is equal to fq, say. Fq belongs to the function space. This also I think you will understand very easily with the analogy of the, not analogy, with the example of position vector. Then this is how the scalar product is defined, dot product. Scalar product is what? Dot product or cross product? Dot product, right. So, scalar product means you take two vectors and multiply them, and what you get is also a vector, right. What you get is a scalars, only magnitude, right. And what we have done is we have worked this out once again for position vectors. What is pi pj? We worked it out and it turns out to be sum over I, the sum over xi xj plus yi yj zi zj, which is basically the same as integral fi star Fj d tau. It's just that in this example we have taken only 3 basis vectors. Okay. So, this is the definition of scalar product. We are going to use this extensively today. So, please do not forget what a scalar product is. Scalar product of Fi and Fj is written as Fi comma Fj in first bracket and is defined as integral Fi star Fj d tau. What is d tau? Volume element. Now, what is a volume element? Yes, Vishnu? What is a volume element? Give me an easy answer. As usual, you are thinking of more difficult answers. I will not even say cube. I will say it is a small volume, right? Small volume somewhere in the function space, right? Small volume somewhere in the function space. I want to define it in such a general manner because then things become very easy for me later on. And when it is very small, right, then what happens is that a little bit of fluctuation does not matter, is not it? If you remember, when you went from Cartesian coordinates to spherical polar coordinates, what is the volume element in Cartesian coordinates? Dx dy dz. What is the volume element in spherical polar coordinates? Everybody knows that, r square sin theta d theta d phi. Is that exactly equal to dx dy dz? Not really, isn't it? Not really, because after all it is a curve and all, but within the approximation that these are both very small, you can say that they are more or less equal. Okay. So, that is what is important to understand. When we talk about volume elements, we are really talking about a tiny volume. So, if we change the coordinate system, it does not matter. The volume element in the original coordinate is the same, can be taken to be the same as the volume element in the transformed coordinate. Do we agree with this? And example is this, your r square sin theta d theta d phi. Dr, I forgot dr, right. R square dr sin theta d theta d phi, very good, right. And then finally what we said is that if out of all these functions that we have taken, if n of them are linearly independent, what is the meaning of linear independence? This is the meaning of linear independence. Sum over I ai fi equal to 0 if and only if ai equal to 0 for every value of ai. Trivial solution, right, which means that you cannot express one of these vectors as a linear sum of the other vectors. And the easiest example once again is E1, E2, E3 or x, y, z, whatever you want to call. So, if you just take x and y, so something into E1 plus something into E2, take the vector sum, where will the vector sum be? Somewhere in the xy plane. Is z axis in the xy plane? No. So, it is impossible for it to exactly offset whatever is the value of z, right. It is not even along z, isn't it? There is no component along z, to be honest, right. That is the meaning of linear independence, that sum over I ai fi can never be equal to 0. The only case where it can be equal to 0 is when ai equal to 0 for all values of I, and if all the coefficients are 0 anyway, then what is it that we are talking about? It is a trivial solution, right, fine. So, formally what we say is if n of the functions are linearly independent, then any of the other functions can be represented as a linear combination of these n functions. Once again, best understood in terms of position vectors and unit vectors, base vectors along the Cartesian coordinates. Take any position vector, how do you write it always? You write the coordinates, right, x, y, z or x1, x2, x3, whatever you want to write. So, no matter which position vector you take, you can represent it completely as a linear sum of the base vectors, right. That is what we are saying here. If n of the functions are linearly independent, in this case 3 of the functions are linearly independent, then any of the other functions can be represented as a linear combination of these n functions, and then the space is called n dimensional. So, our physical space is therefore 3 dimensional, because no matter which point you take in physical space, the position vector of that point can be represented as a linear sum of x, y and z. And finally, what we said is that when do we get orthonormal basis functions? When do we get orthonormal basis functions? we already have linear independence. We already have linear independence, right. So, if these vectors are also orthogonal to each other, like is the case for x, y, z, right, you normalize them, then these are called orthonormal basis functions. And once again, today we are going to deal with some orthonormal basis function. Fine. And then I think this was where we stopped the last day. We had defined something called transformation operators. Okay, nothing to be scared of. Please do not get scared by the term operator and all. It is not all that scary, to be honest. So, what we said is that a transformation operator is something that is going to take a function and then change it. And what we are going to do is we are going to define a transformation operator corresponding to every symmetry operation. For every symmetry operation capital R, we define a transformation operator OR, right. It is just writing the same thing in a different way. What had we defined earlier? With respect to each, not with respect to, for every symmetry operation R, had we not worked out the transformation matrix and had we not called it dr, right, remember capital D and capital R in bracket, right or wrong, dr, remember transformation matrix. Now, all we are saying is that we can write the same thing in an operator form. After all, what is an operator? Operator is something that you do on a function and the function changes. Okay, so we can write as a matrix, we can write it as operator also. Okay, we want to write it in the operator formalism because it makes our task a little easier when we try to derive great orthogonality theorem and in subsequent discussions. That is all. Are we clear so far? For every symmetry operation, we say that we are going to write a transformation operator. And today, for the rest of the day, we are going to talk about some properties of this transformation operator. First property we discussed already, and this is something that is of central importance that keeps coming back to haunt us, that is ORFI in transformed coordinates is equal to Fi in the original coordinates. Makes sense? Makes sense? Because what you do is, if you take the function and perform a C3 rotation or whatever it is, then its coordinates in the original coordinate system would change and the function value would also change. However, if you simultaneously turn the coordinates, then what will happen? There will be no relative displacement, right. So, the function value will not change. So, the transformed function, value of the transformed function in the transformed coordinate system is the same as the original function in the original coordinate system. Make sense? Fine. ORFI is transformed function. Do not get this very clear because this is something that we will use very quickly, very frequently after this. So, please get the physical meaning of transformed function in transformed coordinate being the same as the original function in original coordinate. Sounds like a trivial observation, right? It is not, because the seemingly trivial observation is going to be used later on to prove all the properties of the transformation operators, right. Does it make sense or not? Just say that. Does it make sense? It is just that it sounds silly, right. If you think it sounds silly, then you have got it right. Okay, that means you have understood what it actually means. Okay, it should sound silly if you have understood it at this point of time. Okay, transformed function in transformed coordinate system is the same as the original function in the original coordinate system. All right. Now, may I go ahead? Now, next, this is another thing that is very important to understand the way we write it. OR Fk is equal to sum over j equal to 1 to n djkr Fj. How am I writing the functions? F, F1, F2, F3, F4, F5 dot dot dot, Fk dot dot dot, last is Fn. I write it as a column vector, right. And what is this djkr? That is the matrix element of the transformation matrix corresponding to operation R. What is dr? How did we define dr? dr was the transformation matrix that you worked out earlier for the symmetry operations. Okay. Now see whether this makes sense. What am I doing here? If I say sum over j equal to 1 to n and then I write djk r, what am I doing? d1k, that is the first one, d1k, then d2k. d2k is here or here? Down. d3k, down. d4k, below that, dot 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 dn. So what I have written here is really a column of the transformation matrix. What about fj? fj, so j equal to 1, so djk r first row, sorry, d1k r is first row and which column? Kth column, right? Kth column. Then d2k, which row, which column? Second row, the same kth column. Okay. So that is how we are going down the kth column. And what about fj? When j equal to 1, it is f1, j equal to 2, f2, j equal to 3, f3 and so on and so forth. Now is that how you multiply matrices? Do you multiply column with column? You multiply row with column. Then why are you multiplying column with column now? Why are you multiplying column with column now? Because we are transforming, so do not forget what we had discussed in the last class. Do not forget what we had discussed in the last class. What had we done? First is that we transformed the coordinates, right? And second, we tried to work with the base vectors. So the effect on the base vectors is just opposite, right? Remember what we had shown there? This is your position vector, this is the coordinate system. Now if you rotate like this, if you rotate the position vector like this, which side is it from your direction, clockwise or anti-clockwise? Clockwise. So whether you rotate the position vector clockwise or whether you rotate the coordinate system anti-clockwise, the effect is the same, right? So a transformation that say rotates the coordinates clockwise is going to rotate the base vectors in anti-clockwise manner. So it is going to be the transpose, right? Since we are working with this coordinate, with the functions here, we have to work with the transpose of the transformation matrix. Do not forget that. This is something that we had worked out in the previous class or class before that? Previous class, right? Please do not forget that. So ORFK equal to sum over j equal to 1 to n djk r fj. We are multiplying column by column, but that is because the matrix that we are really working with is the transpose of the matrix that we get from the transformation matrix, right. Please read this from Bishop, understand. If you are not confused the first time, then you have not read it right, alright. Please read this part from Bishop very, very carefully, then only you will understand, and then come back and ask if there is a question. Okay. Do not forget what we are working with. What is f? F is one of the FIs or FJs are the n linearly independent basis functions. So they are like your x, y and z. That is why we have to go down a column, djk not dkj, right. So we are working with the linearly independent basis functions here. Please understand that. It is important, otherwise I mean at your age it is very easy to memorize everything and write it down in the examination, but that does not make any sense. Please understand what is going on. Okay. We are working with n linearly independent basis functions. Do not forget that. We are working with base vectors. Okay. Now, this is something that I am not going to prove, because I think you understand this intuitively anyway, that if T equal to SR, then the transformation matrix dt is a product of transformation matrix ds multiplied by transformation matrix dr. Do you believe me when I say this? T, S, R are the symmetry operations, different symmetry operations. What I am saying is that if T is SR, then their corresponding transformation matrices are also product of each other, dt equal to ds into dr. I think this is something that should come to you intuitively. If not, please look up appendix A.55 Bishop. Okay. So, now the thing is, since that is so, we have shown earlier that the symmetry operations form this representation of the point group, right. So, now we can say that the corresponding matrices also form n dimensional representation of the point group. That is the connection between what we are discussing now and group theory. Remember, we had drawn the group multiplication tables long ago when you were much younger. Huh? So, there if I take any function, so that t equal to SR, what I am saying is that you take the corresponding transformation matrices, multiply them, the transformation matrices will also form the same group multiplication law. You will get the same table if you use the matrices without knowing what is the change. So, first work out the matrices and then without looking at the molecule, just perform matrix multiplication, you will get the same multiplication table, right. So, the matrices themselves form a representation of the group. Are you okay with that? If there is a question, please ask. Do you agree with me that these symmetry operations form a group, right? So, will you believe me if I say that the corresponding transformation matrices that you work out, how do you get the transformation matrices? By using some basis or the other. Let us take any basis. We have taken these n linearly independent basis functions fj, right. Taking those, I have worked out the transformation matrices. So, do you believe me when I say that these transformation matrices will also multiply in the same manner as the actual symmetry operations multiply? If t equal to SR, then d of t will also be equal to d of S multiplied by d of R. This bracket means off, right. So, then what I am saying is that if that is the case, then if I just look at the matrices now, think of C3V. What are the symmetry operations? E, C3, C3 square, sigma V, sigma V, sigma V. For these, if you remember, using x, y, z, which are n linearly independent basis functions with n equal to 3, we had worked out the transformation matrices, right. If I write those matrices side by side, what was the dimensionality of those matrices? What by what? I had used x, y and z as basis. So, I got 3 by 3 matrices, right. I will just remind you of the most difficult matrix of all the three, the matrix for E, right, 1 0 0 0 1 0 0 0 1, okay, very difficult, 3 by 3, right, n equal to 3. So, all the matrices that I had using x, y, z, were they not 3 by 3 matrices? Okay. What was it for say C3, what was it for C3? Huh? I will give you the most difficult line, I will give you the third row, 0 0 1, then minus half root 3 by 2 minus root 3 by 2 half, right, and then rest are all zeros, isn't it. So, once again you got a matrix that was 3 by 3 matrix. So, similarly you got something for sigma v. So, if I write all these matrices side by side, what I am saying is they form a representation of the point group and the dimensionality is n. In the example that I had chosen earlier for C3V, n equal to 3. So, all were 3 by 3 matrices. So, this forms a 3 dimensional representation. I am just stating something that you understood 3-4 classes ago in a little more complicated language. Since you understood it so easily at that time, I am trying to make it a little more confusing now, that is all. Okay. Just think of the example that we have done already, I think it is easier to understand. So, what I am saying is that if you take the matrices, now when I say dr, R is a variable, it is a general operation, symmetry operation, I do not mean this R. So, all the matrices, all the transformation matrices form an n dimensional representation of the point group, alright. And they also form a representation of the group formed by the transformation operators. Once again, it sounds as if I am stating the obvious, but it is important that we believe and understand and then believe what I am talking about now, because it is going to be important later on. So, basically what we are saying is that you take just the symmetry operations, think purely like a chemist, see what is their effect on the atoms and all, and work out a group multiplication table, you get something. Now, take the matrices, perform matrix multiplication, right. So, instead of E write DE, instead of C3 write DC3, instead of C3 square write D of C3 square, instead of sigma b write D of sigma b, so on and so forth, and then carry out the matrix multiplication. Okay. So, you will get the same, exactly the same multiplication table as what you get by using the symmetry operations. Now, if you use the ORs, the operators, transformation operators, then also you get the same multiplication table, that is all we are saying. Okay. So, now if you look at the matrices, the n by n matrices, they form an n dimensional representation of the point group as well as the group formed by the transformation operators. Okay with this? And this is, I think, something you definitely understand. This F1, F2, etc., Fn, they form the basis of the representation, like x, y, z form the basis for C3v or C2v, like that O, HA and HB form basis for C2v.